Presented by Caltech.
So our next lecture is from the world of physics. Jeff Kimble is the William Valentine Professor and Professor of Physics at Caltech. Colleagues in physics say that Jeff has led a revolution in modern physics through his pioneering research in the coherent control of the interactions of light and matter. Kimble is a pioneer in quantum information science, the quantum dynamics of open systems, and founding director of the Institute for Quantum Information and Matter. Now, Jeff and I don't hang out together, sort of like my advantage with Ahmed or Roger or David. So I dropped by Ahmed's office last week. This is a true story. And I said, Ahmed, tell me about Jeff. I know Jeff, he's a colleague, but I don't read your papers all the time, Jeff. True story. So Ahmed got very serious. And then he said in a low, respectful voice, "One atom laser." I felt like I was in a movie script like The Graduate, plastics. All right, so I realized I had to go home and do my homework. So I looked up Jeff's 2003 paper in Nature about a one-atom laser in the regime of strong coupling by McKeever et al. This is a long time ago. I'm sorry, Jeff. Amazing paper. And it had turned out that conventional lasers, as you all know, operate with a large number of intercavity atoms. And so it was only really at the theoretical level that physicists, scientists could think about the lasing properties of a single atom in a resonant cavity. And so it was Jeff that achieved the experimental realization of putting a single atom in a cavity, in an optical cavity, in a regime where one photon was sufficient to saturate the atomic transition. I'll let you explain what you discovered, but it's non-classical, as I recall. Jeff is a Texan, born in Texas, served on the faculty of UT Austin for some years, and joined the Caltech faculty, thank God for us, in 1987. He's received numerous prizes in physics for his pioneering work, and I think we're all excited to hear his lecture titled "The Future of Quantum Physics." Jeff.
Well, it's really an honor for me to be here to celebrate the 2.2 to the 9th seconds. SI units, we've got a representative from National Institute of Standards Technology to certify this. It's really a big event, and I'm really honored to be here. But on the horizon, we have E times 10 to the 9th seconds coming up, and pi times 10 to the 9th seconds coming up. Yeah, I'll explain that in years to the chemists later, okay, other than you, okay? So it's a great honor for me to be here. I've known Ahmed since I came in 1989. His pioneering experiments won his Nobel Prize. I teach to my sophomore class in physics, oscillators, molecules, whatever sort, the quantum mechanics of that process. I followed his invention and development of 4D microscopy. It's just absolutely revolutionary. We've had lots of conversations. I have the greatest respect for Ahmed in the way he addresses science. There's, just what's the core thing you want to do? He suffers no fools, and he has no mean ambition. It's to change the future. He really is a revolutionary in science, and he utilizes, he develops the tools that nobody else has, and that's why he can do these amazing experiments to change the future for us all. I've often thought about collaborating with Ahmed. Here I am, the tall one. Here's Ahmed, and we're on our first experimental adventure in search of not science but food. And I thought the experiment was going okay until Ahmed turns to me and says, I lift, you grab. Was that concept just a little too complex, Jeff? So I can understand the diatomics, but his more recent work. Okay, so we're going to try to look at a little more simple physics in this lecture today. So what I want to tell you about is the natural world, and a part of it that's really in physics, and I think much more broadly impactful in science, what I'll call the entanglement frontier. And it's really the last 20 years, the most exciting time in my career. There are phenomena that we just didn't have a clue about, that all of a sudden seem to be ubiquitous, picking up pieces of things to look at on the one hand, on the other hand, trying to assemble subatomic particles in new ways to find new phenomena. And this entanglement and the field it's given rise to since about 1995 and its explosion is called quantum information science. And it's really broadly impactful in physics and I think in other disciplines, thinking about exotic quantum states of matter, phases of matter. Water is liquid, solid, vapor. Now, there are phases of matter that are qualitatively different and inherently quantum mechanical that are being discovered. That's useful for technologies. Somewhat less useful are black holes. But amazingly, by thinking about black holes, physicists around the world, including John Preskill here, is understanding that maybe entanglement, I'll explain what that is in a moment, is actually the basis for space-time. Ahmed wants to live in 4 dimensions. That's space-time. Where does it come from? Entanglement. Just amazing. And the clues to that have come from studying black holes. So I'll tell you about that. It also, in conceptual terms, but also what's going on in the lab. In the laboratory, theorists come in at 10 or 11, have a cup of coffee, work till 4 or 5, go home. Experimentalists are really up here, scrounging for their lives on these cliffs. So what are the grand challenges in quantum information science? From my perspective, it's the world I live in of single atoms and photons. It's to build complicated quantum systems from the ground up. And it's already clear that by doing that, we will realize in the laboratory physical systems that just have not existed in nature before. Those physical systems will be hard to characterize, difficult to find the secrets inside them, but they will give rise to amazing physical consequences, like a superconductor. One doesn't have to know the microscopic theory to know that if you hook up electrical leads and try to pass current through it, there's something miraculous going on. And furthermore, they can be important, these new kinds of physical systems, to the processing and distribution of information, to measurement, and to something I'll tell you a little bit more about called quantum simulation. So let's get started with some kind of more concrete thing to think about. We have a worldwide network. What if we tried to build quantum networks where inside these little blocks or some kind of quantum thing? You could think of electrons or atoms, some favorite quantum system, and I'll do like this. Quantum system can be here or here. It can be in both places at the same time, like an atom in one of 2 states. And these little blocks where the quantum things live talk to each other over some kind of wire, and the easiest one to think about is just a fiber optic. Photons are inherently, light is inherently quantum mechanical. And the questions, if I handed you something like that I built in my lab and said, does it work? You would be hard-pressed at our current state of knowledge to answer that question. A theorist, if I handed them not the physical system, but the equations, would be hard-pressed to calculate, is it interesting, even in the sense, is it entangled? Does it show this property I'll describe in a moment of quantum entanglement? Never mind, is it inherently useful? So the amazingly exciting thing about quantum information science is this explosion in our ignorance, not our knowledge. And from Texas, that's great. So, experimentally, how do we implement this? I'll tell you a little bit about that, but one of the things we're going to want to do are take states, that's a physical system that has some configuration, and transmit that state somewhere else. And we can't do that on ordinary internet. And so what we're going to try to do is something called quantum teleportation. And the first thing that will come into your mind is the wrong thing. So this is never going to happen that we take people from one place to the other. If you get a subprime loan, you haven't done a very smart thing. If you ever try to walk into one of those, it's the end of your life. Okay, this is future of quantum physics. This is not going to happen in any future that we can conceive. What will happen, I think, in the decades to come are rudimentary internets where we will be able to do things like quantum teleportation. And that's actually useful in a way I won't describe in detail, but if you have a secret, a date, a bank account, and you don't want to share that with anyone, then the quantum world offers ways for security, privacy, that just don't exist in the classical world. Okay, so what is quantum entanglement? There's this little block that has something quantum mechanical inside it, and this little block that has something quantum mechanical in it, and I would like to get entanglement between them. What does this entanglement thing mean? It's inherently quantum mechanical. So let me give it to you in a simple story. Imagine you have a little thread of atoms, just like a hair, a piece of hair. And in this ball of atoms, we're going to send some light in, and we're going to do Raman scattering. And that'll be familiar to physicists, biologists, and chemists. And so this laser comes in and scatters to this level. And when that happens, a photon comes out, and I could detect it. That click means a quantum of light is turned into a photoelectron, and now it's in my microscopic realm. Fine. I could also put another ball of atoms over here, send light in like this, and a photon could come out and be detected. Click. So now, like this, it could happen one way or the other, and I would know this click means here, that click means there. And if I do something as simple as put a mirror, so that light that comes here can go this way or that way, it's just a coherent wave, but it's quantum in character. And now I do the same thing and try to excite this set and that set. What happens is, I can get a click over here. What do I know conditioned on that click? Well, in the quantum world, what I know is one of these ensembles has made that happen. So one atom out of all these, or one atom out of all of those, has transferred. That transfer has happened here or there. And the way that that's written is like this. This is left and right, let's say. So it happened here or there. That's the way it's written quantum mechanically. And that's an entangled state, because you'll ask me, did it happen here or there? And the answer will be yes. Again, in the best Texas tradition. One quantum, we don't know here or there, but it happened at one place or the other. And this is a picture of an experiment that my group did some years ago in 2005 to demonstrate this entanglement. This is a vacuum chamber. This dimension of the vacuum chamber is 20 or 30 centimeters. These were 6 meters apart. And this little thread of atoms is about 100 microns, just like your hair, by about 1 millimeter. And there are about 1 million atoms. And inside of here, there was stored one excitation, and not here or the other way around. So the excitation, and that's what's called entanglement. There was an excitation here or there, and if you ask me which, the answer is yes, both places at the same time. And the amazing thing about the quantum world is it really happens not that your knowledge, I don't know it was here or there, but it's in one place or the other. No, it exists in some crazy way in both places at the same time. And there are measurements you can do to show that. So this is this state again. This is an entangled state of being here and there at the same time. There are possibilities in the quantum world. It's written like that in the quantum language, that you're here. One of them has nothing, the other one has one, or the other way around. And with that, one can then do quantum teleportation. I won't describe the protocol, but if I have entanglement here and here, then I can take other kinds of quantum states and send them from here to there. And we did an experiment like that, teleportation, some years ago, again, in the lab across campus, where what we did, that's a picture of the experiment, there's, in the conventional language, an Alice who receives an unknown quantum state. It was beam of light in our case. This is the quantum fuzz on the beam of light. And Alice made a measurement of that state and destroyed it, and then took the answer and sent it over here. That alone is not sufficient to recreate the state. Alice and Bob have to, ahead of time, share this quantum entanglement, for example, in the way I just showed you. So if, like the magician, you look here and you say, okay, there was a state and it popped out over here, it must be somewhere in between. No, this happened before the state was ever sent, and you can show that the information in this quantum channel, it's just a fiber optic or a smoke signal, whatever, is just completely random classical bits. So how did you get from here to here? You know, it's like the magician sawing the person in half, you know. So it's useful for quantum internet, for quantum networks. That simple idea of entanglement can be extended to what's called a quantum computer, which has provably more capable possibilities than classical computers. So a quantum state is, imagine that I have this thing like this, and I have k of them, 10 or 20, and they're all down, that's 0. Or if they were all up, that would be all 1s. And in fact, that you can make a quantum state where all those possibilities exist simultaneously. And so then that's the state, that's the data that you want to send into a quantum computer. This looks more like a chemist than a physicist, but anyway. And there's a quantum computer, and then you get something out. And what you want to do is evaluate a function on this input. So you want to take an input of your budget and get out whether you're going to be over or under your budget. And so this is the output state. It's this function because quantum mechanics is linear operating on each one of these states. And so the magic of this is, normally if you want to calculate 2 squared, so you type that in your computer and you get 2 squared, 2. And then you want to calculate 3 squared and 4 squared, the same function. You have to do that over and over and over. In this case, if there are k bits, if k were 100, then you can't even write this state down, much less compute it. It takes more particles than there are in the universe to write it down. So quantum computing is powerful because all possible input data are computed in parallel. So that sounds kind of neat to have. Nobody has one. We think we know how to build them. There have been pioneering contributions made at Caltech. But if you want to go on the web and buy one, and you have $100 million, then you can believe the publicity. They're good graphics, and they sell the most advanced quantum computers in the world, D-Wave. Google has invested in this and has one there. And you know, you can meet them, you can admire them, and you can go home and do quantum computing. So you can go that route, which is actually in the current world fairly controversial about whether this machine is really quantum and in what way and how it has advantages. There are papers written about that. But it's somewhat problematical because nobody really knows what's inside of there. Or you can go to the scientific literature, this by Michel Devereux and Rob Sholkoff, 2 leaders in trying to build really one piece at a time, complicated quantum machines. And just to tell you, it looks kind of simple. This piece of aluminum can be superconducting. And inside of here is a Josephson junction, something from superconductivity. And what these authors have demonstrated in the quest to really build a quantum computer, where the current state of the art is maybe this many quantum things up and down at the same time, are photons stored in here for quantum memory. And this is some complicated representation of what photons look like in quantum mechanics, and the fact that it has 2 colors tells you that it's really quantum mechanical, roughly. Okay. Quantum computers, in my view, if you've already invested in D-Wave, hold your ears. Quantum computers capable of doing things like attacking public key cryptography. That's something called Shor's algorithm, after Peter Shor, who won the Distinguished Alumni Award at Caltech some years ago, are really large-scale special purpose computing machines. They would revolutionize the world because all the known protocols for providing security would be vulnerable. But in my view, the future of quantum physics, that's decades away. It's a great intellectual and technical adventure for the people involved in it. And it's not at all clear the pathways. It's not, we know what to do, and then we just have to get more money. So that's wonderful. But a much nearer term, I think in the coming decade, will be quantum simulation. Now, what's quantum simulation? Quantum simulation was introduced by Richard Feynman, and he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make a quantum mechanical. And by golly, it's wonderful, and it doesn't look so easy. And he wrote a somewhat more quantitative analysis of quantum simulation. It's to try to get one physical system to emulate another. We've got this complicated physical system we don't understand, but we have, say, atoms and photons, and we know how to control those, so we'll make this physical system emulate that one so we can understand it. Seth Lloyd, who was a postdoc at Caltech with Murray Gell-Mann, substantiated parts of Feynman's vision. And then more recently, John Preskill and his colleagues extended these ideas to quantum field theory. So if you think about CERN and high energy particle physics, the most exotic frontiers of physics can, even with atoms and photons, be efficiently simulated. So why would you want to simulate? You'd like to simulate because there's this complicated thing like a high-TC superconductor or some other something that could be of value for society, for technologies. We don't understand it. We have to have scientific understanding to develop engineering disciplines, quantum technologies. So this simulation, I think, will be useful in the coming decade. We'll be able to simulate things that you could not otherwise understand. So that's described in two pioneers in this area, Ignacio Serac and Peter Zoller, who were both Moore scholars at Caltech in years past. Okay, so you'll hear more about this subject from the lecture of Bill Phillips, who's helped found the whole area 25 years ago. This bumpy little egg carton is made by just putting two waves together, and that makes interference. And if you put two waves together like that, it makes interference, so you can make this 2D egg carton. And these are single atoms, pictured. They could all be rubidium, say. And the difference between this yellow and the red is simply some state inside. One of them's this way, one of them's that way. Or they could be different atoms, rubidium and potassium. So lattices like that, almost perfectly filled, almost perfectly motionless, controlled in all their degrees of freedom. What can you do with them? Manuel Indras was a student of one of the leading groups in the world at the Max Planck Institute outside of Munich, and did an experiment that's really simple. You take it some initial state of spins. Remember, states in quantum mechanics, if they're internal states of the atom, say, can be this way or that way. So it's just 0 or 1. It's thumbs up, thumbs down. Except in the quantum world, it can be up and down at the same time. And you take some initial state where they're all spin up, and it's really a chain of individual atoms that are individually addressable. Unlike in the condensed matter world, that's really hard to achieve, where you have control over all the quantum degrees of freedom. And you suddenly flip to the blue spins down. What happens? Well, this excitation is going to migrate. That's the magnon that's described, magnon bound states. And how are these two spins? Are they going to hop together, or are they going to hop one by one? And as they hop, if the initial state is an entangled state, what happens to the entanglement? If they hop separately or even together, that turns out to be, in this toy cartoon, you can have my new granddaughter play a game like that, but in the quantum world, that's fiercely difficult to simulate on a classical computer. So I think we will have serious quantum simulations in a variety of areas, cold atoms, ions, single trapped ions, in the decade to come. The kind of thing that we've been working on at Caltech, we as Oscar Painter and myself, is a different approach to this whole business of how do we build quantum systems, whether for simulation or some other way, and that's to try to combine nanophotonics, tiny little nanophotonic devices. The dimensions are hundreds of nanometers, 200 nanometers scale. Light propagates just like in an optical fiber, essentially lossless, of very high quality factors. They're really interesting. We have powerful capabilities in the Kavli Nanoscience Institute here to build these things, but they're kind of bland. Unless you give them quantum functionality. How do you do that? Use single atoms. It seems crazy to take, this is tiny, but an atom is even tinier. How can one atom influence light propagation, photon by photon, in this giant dielectric? It can, and we've already achieved that in our first efforts. So imagine just light trying to propagate along like that. We've achieved atoms trapping where one photon comes to one atom and the transmission coefficient is 0.25. 25% of the light gets through, 75% reflects. Amazing, by single atoms. And you know that single atoms can be this way or that way. So if the atom's this way, it reflects. If it's that way, it transmits, and conversely. So just send a pulse of light in, and it acts as a beam splitter, and the light's automatically entangled. So this is the kind of thing we've built, first in one dimension. This is an optical fiber. This is all complicated. The star of the show is right here. We call this an alligator photonic crystal waveguide, maybe for obvious reasons. This dimension is about 350 nanometers. The wavelength of visible light is 600 nanometers. So these are tiny, tiny devices. A lot of technical pain went into learning how to do these by Oscar's group and mine. And this is what one looks like in a SEM. Isn't that amazing? We wiped the blood of the graduate students and postdocs off. This has been an incredibly demanding endeavor that people told us in nanophotonics you'll never make happen. But we have, and not only have we built them, we've trapped atoms and we've done physics. And to tell you about that, I want to introduce Challeng Hung, who's just this amazing postdoc from beginning to end of his time at Caltech, who's created a really new future for atomic physics with photons.
So what you see here is a source for atoms. We try to create a pipe that guide the photons and the atoms into that pipe. So there's no way they can avoid each other. They have to interact. So how do we do that? The way we do it is it generates a cloud of cesium atoms. We shoot it to the center of the chamber, and we create 6 laser beams. Inside this laser field, they form some kind of molasses. No matter which direction it goes, we always trick the atom, so they keep losing energy. Its motion gets damped, and then it moves very, very, very slowly. This chip sits at the center of the chamber. In this window, there's a 200 nanometer thick, 300 nanometer wide. We call it alligator waveguide. The reason is because it's 2 parallel beams, and then it's the inverse of the alligator shape. So this shape might look very weird, but we use these teeth to create a situation that when photons propagate along the waveguide, all these teeth, they create interference, then the speed of light is slowed down. And the intensity of photons is strong here, weak here, strong here, weak here, strong here. When atoms see strong intensity, it gets kicked out by the photon. It has repulsive force. So we can guide this atom into this kind of dark spot here. At the same time, we can send another frequency of light, which brights up at the dark spots. It's the magic of this kind of alligator waveguide. So we achieve both guiding the atom and then have them interact strongly with the photon. Otherwise, it would be like atoms are flying around and I shine a big white flashlight, just hope that my flashlight can hit the atom. But using this kind of lithographically patterned waveguides, we can create an array of these tiny little traps. So if one atom gets excited, it emits a photon. This photon can travel down to the waveguide, talk to another atom. And then this atom changes the property of this photon and then again propagate down the waveguide and then talk to another atom. By doing this, we can create a quantum simulator of many, many quantum objects interact with each other. And then if I just let the system evolve, what would the answer be?
So that's our take on the future in one dimension. But you know there's more than one dimension. So we've analyzed this in 2 dimensions. This is a artist's conception of atoms. These little holes are a 2D photonic crystal, it's called. It has crystalline structure and band gaps, just like regular crystals, but now for photons. And what we're trying to do is really make quantum dielectrics. My glasses, window panes, all are classical dielectrics. We would like dielectrics, like plastics in the graduate, to have properties which depend on the photon number, 1, 2, 3. It would be a real revolution in the ability to manipulate and control light coherently. We know and we predict in here exotic quantum phases of light and matter that we could build. What would their properties be? Well, I hope we'll find out. These kind of systems will be useful for kind of all the things I've told you about. And while that's the cartoon, we're busy in the fab. This is real, this gray structure, silicon nitride in a hexagon lattice. The green is my dream. We're going to get atoms in there, though. And that will allow us to do really interesting things in 2D, including new topological phases of matter. So, quantum computing, quantum simulation, what about quantum measurement? We need to measure stuff in society. How about using clocks? GPS is good, not good enough. Here's a clock which works at a part in 10 to the 18th. And this is done by Junier, who is a prize postdoctoral fellow at Caltech in my group. I think that's Dr. Bill Phillips' liquid nitrogen venting, you know. Could you vent elsewhere? Could you vent elsewhere? Anyway, this is the cloud of atoms. That's going to be the clock. And this, you won't know, this is the inaccuracy of the clock as a function of how long you look. And this line that are the measurements has never been seen before. This line reaches a part in 10 to the 18th in 10 to the 4 seconds. So in a few hours. And it's, for example, 3 orders of magnitude. A factor of 1,000 doesn't come that often in metrology. 1,000 better than previous clocks. And there's no reason that this won't go another 2 orders of magnitude. So great, that's metrology. What does it have to do with this quantum stuff I've been telling you about? Well, Junier and his colleagues know that here are all these atoms, and every chemist knows about dipole-dipole interactions. Well, they're tiny if you put them a micron apart. No, they're not when you want 10 to the minus 19 frequency shifts. So these molecules by themselves become quantum mini-body systems. So quantum mini-body systems meets metrology, meets new quantum phases of matter. If you'd like to measure big G, remember Newton told us about that. 2 masses, the force is proportional to the product of masses, the inverse distance squared, and a constant. That constant is a shame, a source of embarrassment in physics, especially if you work at NIST. All the fundamental constants, you know, the gram, the kilogram is measured to a part in 10 to the 9th. People are trying to make it a part in 10 to the 10th. This is known not even to a part in 10 to the 4th. Why is that? People work, these are really all amazing experimentalists, and you can say, well, these are big error bars, but in recent years, these measurements are way out of the range. And now atoms enter, quantum version of trying to figure out big G. Maybe it can remove this conundrum. Even a broader perspective on what does this entanglement have to do with anything? A and B are trying to measure something. This is the thing they want to measure in between. And pioneering work about what are the limits to doing that. They're called the standard quantum limits. Were done by Vladimir Berginsky, a long-time visitor at Caltech, Kip Thorne, his student Carlton Caves. And they formulated strategies for avoiding these so-called standard quantum limits. Why would you ever want to have here and here something and something in the middle? Well, if you're trying to detect gravity waves, you've got 2 mirrors in an interferometer and the gravity wave goes through. And the sensitivity limit that LIGO will soon reach is associated with quantum noise. And like it or not, when the lasers go in and come out, the motion of the mirrors is entangled with the light that comes out. So in the next decade, I predict that LIGO will do yet 10 times higher event rates just because they use quantum resources. Okay, so the broader impacts of quantum information science on society. There are lots of, I think, impacts to help explore new paradigms for information science. It's the basis of much of our civilization. by contributing to the foundations of quantum technologies. Most importantly is human capital, young people. And people are really interested in this stuff. Even if you'd like to teleport people, and it's crazy, people pay attention to quantum teleportation. The other thing I would like to make is, a comment I'd like to make, and maybe a little bit extended remark is, I believe that science is critical to human civilization, and there's the direct, tangible benefits that accrue from scientific advances. But I believe that science communities around the world are a strong stabilizing role in the world against the basic tribal instincts of mankind. Science helps hold us together, appreciates our sameness and not our differences. That said, how do we best ensure that science remains vigorous, positive asset to civilization? There's the kind of obvious, the young people have to learn. Science gets more and more complicated, there's more and more to learn. The tools of the trade have to be passed on. Every scientist must ensure that by whatever means, science was handed to her, and she has to do better than I did at passing it to the next. Everybody's job is to preserve and improve science. But by far the most important element in this process is the transmission and strengthening of the integrity of science. Our integrity as a community is like our virginity. You lose it, it's gone. So, you know, a weak moment has consequences forever. So this article is, I think, very thoughtful by Dr. Alberts and colleagues about integrity in science and how do we do better. We always have to do better. There are pressures in the society. And so one point that hasn't been stressed, I think, that I'd like to mention begins with this article by Dan Kleppner. This was a nuclear physicist who served on publication committees, editorial oversight, and he wondered about costs of publication. And he found out that Gordon and Breach, you might remember them, had costs that ranged up to 40 times the cost of the AIP. So he wrote an article in Physics Today, a couple of articles, and he was sued for a decade. So was the AIP. He was hounded to death in every court around the world. There's a longer story about this that's good. The point I need from this is provide a cautionary tale on what can go wrong when science and commercial enterprise collide. Okay. This is a wonderful document I get once a year. It's really glossy and nice. It comes from Nature, which had been Macmillan, now Springer. It's a company. And in it, they tell us in the Nature Index that it's a global indicator of high quality research. Great. We do high quality research here, lots of time. So let's have a look at that. Where is Caltech on their list of high quality research institutes? Well, we're down here at number 20. And we're ranked according to some kind of weighted fractional count. What the heck is that? It's science by the kilogram. They count up the number of papers, and if you got a lot of them, you live up here, and if you have a few, you live down here. Okay, but nonetheless, we're 20th. So surely there are better departments at Caltech? Well, yeah, 7 in Earth and Environmental Science. Well, that must mean there's some that are lower than the mean. This is physical science. Chemistry, I hate to show. We're going down. Given the sometimes conflict of biologists and physicists, well, what can I say? You know, biology's not even in the top 50. So what can you say about that? You know, this is serious. Nature is a serious, powerful influence in the world. They have resources that dwarf the American Institute of Physics that publishes the papers you know, for the physics community. What can you say about that? Nature is, by this measure that Carl Caves attacks, called impact factor, how many citations per article. Nature lives at the top of the food chain. what had been in physics the premier journal, I was very happy that LIGO's results were published there, is Physical Review Letters is 7.8, Nature Physics is 2042. What can a young person conclude except I better be up here? There are departments in China where a publication in Nature guarantees your tenure. There are strong, serious pressures from this commercial enterprise, and we can laugh at this shiny booklet. It's just garbage, but it sets trends for science. It sets trends for science. So what do we do about that? Well, the solution is going to be some rugged trekking. I believe strongly, never mind Nature, I'm off on them, that the journals, Nature is a magazine. We have journals. Our strength are scientific societies, and we must establish control of the publication process. We have to be involved. What weapon do we have against commercialism? It's ourselves. It's scientists. Who referees for Nature? It's us. We need to use to our benefit our societies, and that means that I have to work harder than I have. It's not the young people's job as much as it is mine. And how many of you have ever read a comment in Nature or Science? In the old days, it was more common. Now it's not. I believe that 10 or 20% of the resources of a journal should be devoted to a vigorous critical exchange. The people who referee that, the editors, are inherently conflicted. If I'm the editor of a paper, I can't review the criticism of that paper. If I'm the referee of a paper that was published, I can't be the referee. So it's more resources, more of my time. But we have to, the pressures, I think, mount and become stronger and stronger at a corrosion of scientific integrity through the commercialism and our busy schedules. And, well, Nature's not all bad. A tragedy of eras. Peer-reviewed papers, easy to find, but how do we fix them? So there is a debate about this, and we all need to be involved. It really is, I think, an important part of the future of science, and science is important to society. So, doesn't make so much difference to me. It's the young people. My job is to pass along the integrity of the enterprise. Everything I told you about from my group, it's just amazing to me that these young people devote with such energy the core of their youth to science. Okay, finally, Ahmed, thank you for more than I can say. It's been one of the highlights of my life to know you at Caltech. My life, lives of others, are all the better for so many of us because of you. And 70 laps around the sun is no mean feat. I'm very happy and look forward to many more laps. Thank you.